Welcome once again to this interesting series of visual classes. Today, we are here to study yet another topic from the lesson Electric Current and Resistance. Dear students, electric current and resistance ਦੇ lesson ਵਿੱਚੋਂ grouping of cells ਦੀ ਇਸ class ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਅਸੀਂ ਸਿੱਖਾਂਗੇ ਕਿ ਰੈਜ਼ਿਸਟੈਂਸਸ ਅਤੇ ਕੈਪੈਸਿਟਰਸ ਦੀ ਹੀ ਤਰ੍ਹਾਂ ਦੋ ਜਾਂ ਦੋ ਤੋਂ ਵੱਧ ਬਿਜਲਈ ਸੈੱਲ ਵੀ ਇੱਕ ਦੂਜੇ ਨਾਲ ਦੋ ਵੱਖ ਤਰੀਕਿਆਂ ਨਾਲ ਕੰਬਾਈਨ ਕੀਤੇ ਜਾ ਸਕਦੇ ਹਨ। ਮੰਨੀ ਗੱਲ ਹੈ ਕਿ ਸੈੱਲਾਂ ਨੂੰ EMF ਦੀ ਓਰੀਜਨਲ ਵੈਲਿਊਜ਼ ਤੋਂ ਹਟ ਕੇ ਕਿਸੇ ਹੋਰ ਡਿਜ਼ਾਇਰਡ ਵੈਲਿਊ ਨੂੰ ਪ੍ਰਾਪਤ ਕਰਨ ਲਈ ਕੰਬਾਈਨ ਕੀਤਾ ਜਾਂਦਾ ਹੈ। Let us begin in detail with two cells in series combination.
The diagram shown here has two cells connected in series. The two cells are said to be connected in series between 2 points A and C if one terminal of each cell is joined together and the second terminal of each cell is free. Let E1 and E2 be the EMFs of the two cells, and R1 and R2 be their internal resistances respectively. Let the cells be sending the current I in a circuit. Let VA, VB and VC be the potentials at points A, B and C respectively, and I be the current flowing through them. Then, the potential difference between positive and negative terminals of the first cell is VAB equal to VA minus VB, which is also equal to E1 minus IR1. Potential difference between positive and negative terminals of the second cell is VBC equal to VB minus VC, which is also equal to E2 minus IR2. Thus, potential difference between A and C of the series combination of the two cells is VAC equal to VA minus VC equal to VA minus VB plus VB minus VC, which is also equal to E1 minus IR1 plus E2 minus IR2. On simplifying, this can be written as E1 plus E2 minus I into R1 plus R2. Let this be equation 1. If the series combination of two cells is replaced by a single cell between A and C of E equivalent and internal resistance R equivalent, then VAC is equal to E equivalent minus I into R equivalent. Let this be equation 2. Comparing equations 1 and 2, we have E equivalent equal to E1 plus E2 and R equivalent equal to R1 plus R2. If n cells of EMFs E1, E2, E3 and so on up to En and of internal resistances R1, R2, R3 and so on up to Rn respectively are connected in series between A and C, then their equivalent EMF, E equivalent is equal to E1 plus E2 plus so on up to En. And equivalent internal resistance of the cells is R equivalent is equal to R1 plus R2 plus so on up to Rn. So, the main rules for the series combination of cells are: number 1, the equivalent EMF of a series combination of cells is equal to the sum of their individual EMFs. And secondly, the equivalent internal resistance of a series combination of cells is equal to sum of the individual internal resistances. It is also to be noted that in the series combination of two cells, if negative terminal of first cell is connected to the negative terminal of the second cell between points A and C, as shown in this diagram, then VBC is equal to VB minus VC equal to minus E2 minus EIR1. Then equivalent EMF of the two cells is E equivalent equal to E1 minus E2. And the equivalent internal resistance is R equivalent equal to R1 minus R2. ਹੁਣ ਦੋ ਸੈੱਲਾਂ ਦੇ ਪੈਰਲਲ ਕੰਬੀਨੇਸ਼ਨ ਦੀ ਗੱਲ ਕਰਦੇ ਹਾਂ। If positive terminal of each cell is connected to a point A and negative terminal of each cell at the other point C, as shown in this diagram, the two cells are said to be in parallel combination. Let the cells be sending the current in a circuit which is not shown here. Let E1 and E2 be the EMFs of the two cells, and R1 and R2 be their internal resistances respectively. Let the currents from the two cells flow towards point B1 and I be the current flowing out of B1. As charge flowing in is equal to charge flowing out, it can be written as I1 plus I2 equal to I. Let this be equation 1. Let VB1 and VB2 be the potentials at B1 and B2 respectively, and V be the potential difference between B1 and B2. Here, the potential difference across the terminals of first cell is equal to the potential difference across the terminals of the second cell. So, for the first cell, V is equal to VB1 minus VB2, which is equal to E1 minus I1 R1, or I1 is equal to E1 minus V upon R1. For the second cell, V is equal to VB1 minus VB2, which is equal to E2 minus I2 R2, or I2 is equal to E2 minus V upon R2. Putting values of I1 and I2 in equation 1, we get I equal to E1 minus V upon R1 plus E2 minus V upon R2. This is equal to I equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. On simplifying, this turns out to be I equal to E1 R2 plus E2 R1 by R1 R2 minus V into R1 plus R2 by R1 R2. Or V is equal to E1 R2 plus E2 R1 upon R1 plus R2 minus IR1 R2 upon R1 plus R2. This is equation 2. If the parallel combination of cells is replaced by a single cell between B1 and B2, of EMF E equivalent and internal resistance R equivalent, then V is equal to E equivalent to minus I into R equivalent. Let this be equation 3. Comparing equations 1 and 2, we have E equivalent equal to E1 R2 plus E2 R1 upon R1 plus R2. We will name this as equation 4. And R equivalent is equal to R1 into R2 upon R1 plus R2, or 1 upon R equivalent is equal to R1 plus R2 upon R1 into R2, which is equal to 1 upon R1 plus 1 upon R2. Dividing equation 4 by equation 5, we get E equivalent upon R equivalent equal to E1 R2 plus E2 R1 upon R1 R2. This is equal to E1 upon R1 plus E2 upon R2. If n cells of EMFs E1, E2, E3 and so on up to En and internal resistances R1, R2, R3 and so on up to Rn are connected in parallel, whose equivalent EMF is E equivalent and equivalent internal resistance is R equivalent, then 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus and so on to plus 1 upon R1. And E equivalent upon R equivalent is equal to E1 upon R1 plus E2 upon R2 plus and so on to plus En upon Rn. And now, if the two cells connected in series are of the same EMFs and the same internal resistances, then E equivalent can be written as equal to ER plus ER upon R plus R, which comes out to be equal to E. Also, 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R equal to 2 upon R. And an interesting fact about the parallel combination of identical cells is that the equivalent EMF of all cells is equal to the EMF of one cell. This happens simply because in parallel combination of cells, there is only increase in sizes of the electrodes and not the EMF of the cells. Equivalent internal resistance of parallel combination of n cells can be written as 1 upon R equivalent equal to 1 upon R plus 1 upon R plus and so on up to n terms, finally equal to n upon R. Or you can say R equivalent is equal to R upon n.
So far in this lesson, we have learned about the grouping of two cells in series as well as in parallel combinations. I will now discuss the condition of grouping of a number of identical cells. Grouping of a number of identical cells. There can be three types of grouping of identical cells. Cells can be in a series combination, cells can be in a parallel combination, and cells can be in a mixed grouping. Let us handle them one by one. I'll first take up the case of cells in series. grouping of a number of identical cells in series. When n identical cells, each of EMF E and internal resistance R, are connected to the external resistor of resistance R as shown in this diagram, then the cells are connected in series. EMF of n cells in series, E equivalent is equal to E plus E plus E up to n terms, equal to n times E. Equivalent internal resistance of n cells in series. Hence, the total resistance of the circuit is equal to NR plus capital R, that is the resistance of the external resistor in the circuit. Current in the resistance R is given by I equal to NE upon NR plus capital R. Now, there are some special situations possible. Let us look at these also. The first possible special case can be that the resistance of the external resistor in the circuit be very small then as compared to NR. Then R can be neglected in comparison to NR. We can now write I equal to NE upon NR, which is equal to E upon R. Thus, the current in the external resistor is the same as due to a single cell. Then, the second special case can be that the resistance of the external resistor in the circuit be very large than as compared to NR. Then NR can be neglected as compared to R. So, I is equal to NE upon capital R. Thus, the current in the external resistor is N times the current due to a single cell. From this, we conclude that the maximum current can be drawn from the series of combination of cells if the value of external resistance is very high as compared to the internal resistance of the cells. This was all for the series combination of identical cells. We will now consider the case of grouping of identical cells in parallel. Let there be m identical cells, each of EMF E and internal resistance R. Let them be connected to the external resistor of resistance R as shown in this diagram. Then the cells are connected in parallel. As the cells are connected in parallel, their equivalent internal resistance 1 by Rp is given by 1 by Rp equal to 1 by R plus 1 by R plus and so on up to m terms. This becomes equal to m by R, or Rp is equal to R by m. As R and Rp are in series, the total resistance in the circuit is equal to R plus small r by m. In parallel combination of identical cells, the effective EMF in the circuit is equal to the EMF due to a single cell, because in this combination only the size of the electrodes increases, but not the EMF. Therefore, current in the resistance R is given by I equal to m into E upon mr plus small r. Students, just like the case of series combination, there can be two special situations for parallel combination as well. The first of them is that the resistance of the external resistor in the circuit be very small then as compared to R. Then MR can be neglected as compared to R. For case 1, I is equal to ME upon R. Thus, the current in the external resistance is M times the current due to a single cell and R can be neglected. Then the second special case can be that the internal resistance of the external resistor in the circuit be very large than as compared to MR. Then small r can be neglected as compared to MR. Thus, I will be equal to M into E upon M into resistance of external resistance. Hence, the current in the external resistance is the same as due to a single cell. इथों ਇਹ ਸਿੱਟਾ ਕੱਢਿਆ ਜਾ ਸਕਦਾ ਹੈ ਕਿ ਜੇ ਸੈਲਾਂ ਦੀ ਐਕਸਟਰਨਲ ਰੈਜ਼ਿਸਟੈਂਸ ਉਹਨਾਂ ਦੀ ਇੰਟਰਨਲ ਰੈਜ਼ਿਸਟੈਂਸ ਨਾਲੋਂ ਬਹੁਤ ਘੱਟ ਹੋਵੇ ਤਾਂ ਪੈਰਲਲ ਕੰਬੀਨੇਸ਼ਨ ਵਿੱਚੋਂ ਮੈਕਸਿਮਮ ਕਰੰਟ ਡਰਾ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਇਹ ਤਾਂ ਸੀ ਸੈਲਾਂ ਦੇ ਸੀਰੀਜ਼ ਐਂਡ ਪੈਰਲਲ ਕੰਬੀਨੇਸ਼ਨਸ ਬਾਰੇ ਡਿਸਕਸ਼ਨ, ਪਰ ਇਸ ਦਾ ਮਤਲਬ ਇਹ ਨਹੀਂ ਹੈ ਕਿ ਇਲੈਕਟ੍ਰੀਕਲ ਸੈਲਸ ਸਿਰਫ ਸੀਰੀਜ਼ ਜਾਂ ਪੈਰਲਲ ਕੰਬੀਨੇਸ਼ਨਸ ਵਿੱਚ ਹੀ ਕੰਬਾਈਨ ਕੀਤੇ ਜਾ ਸਕਦੇ ਹਨ। ਇਹਨਾਂ ਨੂੰ ਕੰਬਾਈਨ ਕਰਨ ਦੀ ਇੱਕ ਹੋਰ ਸੰਭਾਵਨਾ ਹੈ ਜਿਸ ਨੂੰ cells in mixed grouping ਕਿਹਾ ਜਾਂਦਾ ਹੈ। If the cells are connected somewhat as shown in this diagram, they are said to be connected in mixed grouping. Let there be n cells in series in one row and m rows of cells in parallel. Suppose all the cells are identical. Let each cell be of EMF E and internal resistance R. In each row, there are n cells in series. Therefore, their total internal resistance is equal to n into R. Their total EMF is equal to n into E. Since there are m rows of cells in parallel, therefore, total internal resistance, that is Rp of all the cells, is given by 1 upon Rp is equal to 1 upon Nr plus 1 upon Nr plus up to m terms. This becomes equal to m upon Nr, or Rp is equal to Nr upon m. The total resistance of the circuit becomes equal to capital R plus Nr by M. Since the parallel combination of cells does not affect the EMF of the cell, but simply increases the size of the electrodes. Therefore, the effective EMF of all the cells is equal to NE. The current in the external resistance R is given by I equal to NE upon capital R plus NR by M, which is equal to M into N into E upon MR plus N into small r. The current I will be maximum if MR plus NR is minimum, that is under root MR whole square plus under root NR whole square minus 2 root MNR into small r plus 2 root MNR small r is equal to minimum, or under root MR minus under root NR whole square plus 2 root MNR small r is equal to minimum. This will be so if the under root MR minus under root NR is equal to 0, or under root MR is equal to under root NR. It can also be said that Mr is equal to Nr, or the resistance of the external resistor R is equal to Nr upon M. That is, external resistance equal to total internal resistance of all the cells. Thus, we get the maximum current in mixed grouping of cells if the value of external resistance is equal to the total internal resistance of all the cells. Dear students, whatever we have learned regarding the grouping of cells today has some significant aspects which need attention and must be kept in mind while working for these combinations. Come, let us give a thought to these once again. When n identical cells, each of EMF E and internal resistance R are connected in parallel, the total EMF of the cells is E. Since the parallel combination of cells increases the size of the electrodes and does not change the EMF of the cell. When n identical cells, each of EMF E, are connected in series, the total EMF is equal to Ne. When one cell is wrongly connected in series of n identical cells, each of EMF E, it will reduce the total EMF by 2E. That is, the effective EMF is equal to Ne minus 2E. When n cells, each of internal resistance R, are wrongly connected in series, the total internal resistance of the cells is equal to Nr. That is, there is no effect on the total internal resistance of the cells. It can be concluded that the cells are connected in series to get more voltage. The cells are connected in parallel to get more current. The cells are connected in mixed group to get more power. It has been enough of learning for today. Let us now summarize the lesson. When two cells are connected in a series combination, then firstly, the equivalent EMF of a series combination of cells is equal to the sum of their individual EMFs. And secondly, the equivalent internal resistance of a series combination of cells is equal to the sum of the individual internal resistances. When two cells of EMFs E1 and E2 and internal resistances R1 and R2 are connected in parallel combination between 2 points, then we have E equivalent equal to E1 R2 plus E2 R1 upon R1 plus R2, and R equivalent is equal to R1 into R2 upon R1 plus R2. A number of identical cells can be combined together. There can be three types of grouping of identical cells. They can be combined either in a series combination or in a parallel combination or even in a mixed grouping. We get the maximum current in mixed grouping of cells if the value of external resistance is equal to the total internal resistance of all the cells. It can be concluded that the cells are connected in series to get more voltage. The cells are connected in parallel to get more current. The cells are connected in mixed group to get more power. ਚਲੋ ਹੁਣ ਤੁਹਾਨੂੰ ਕੁਝ ਸਵਾਲ ਪੁੱਛ ਕੇ ਵੇਖਦੇ ਹਾਂ ਜਿਹੜੇ ਅੱਜ ਪੜ੍ਹੇ ਵਿਸ਼ੇ ਤੇ ਬਣੇ ਤੁਹਾਡੇ ਆਪਣੇ ਭਰੋਸੇ ਨੂੰ ਹੋਰ ਪੁਖਤਾ ਕਰਨਗੇ। ਇਹਨਾਂ ਸਵਾਲਾਂ ਨੂੰ ਧਿਆਨ ਨਾਲ ਸੁਣਨਾ ਅਤੇ ਸੋਚ ਸਮਝ ਕੇ ਜਵਾਬ ਦੇਣ ਦੀ ਕੋਸ਼ਿਸ਼ ਕਰਨਾ। ਪਹਿਲਾ ਸਵਾਲ ਹੈ, what is the condition for drawing the maximum current in mixed grouping of cells? The answer is, we get the maximum current in mixed grouping of cells if the value of external resistance is equal to the total internal resistance of all the cells. अगला सवाल, what is the expected outcome of connecting cells in parallel? The answer is, the cells connected in parallel give more current. ਹੁਣ मैं इस आस नाल पाठ की समाप्ति करती हाँ कि तुसी सारिਆਂ ने इस पाठ का पूरा लाभ लिया होना है ਅਤੇ ਇਹ ਇਮਤਿਹਾਨਾਂ ਵਿੱਚ ਵੀ ਤੁਹਾਡੀ ਮਦਦ ਕਰੇਗਾ। ਪਾਠ ਤੇ ਧਿਆਨ ਦੇਣ ਵਾਸਤੇ ਸਾਰਿਆਂ ਦਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਤੱਕ ਗੁੱਡ ਬਾਏ ਐਂਡ ਸੀ ਯੂ ਅਗੇਨ ਵਿਦ ਸਮਥਿੰਗ ਨਿਊ।